Hey there, science fans! Today, we're diving into the fascinating world of limits in calculus. Don't worry, it's not as scary as it sounds. Imagine you're driving towards a big, beautiful mountain. You can get closer and closer, right? That's kind of like a limit. In math, a limit tells us what happens to a function, think of it like a math rule, as we get closer and closer to a specific input value. It's like asking, what happens to this equation as we sneak up on this particular number? Think about a hot cup of coffee. As time passes, the coffee cools down, getting closer and closer to room temperature. The limit in this case would be the room temperature, the value the coffee's temperature approaches over time. Limits are super useful because they help us understand how functions behave, even when things get a little weird or undefined. They're like mathematical detectives, helping us solve mysteries about how things change and interact. Limits aren't just some abstract math concept, they're everywhere in the real world. Let's take a look at a few examples. Imagine you're filling a balloon with air. As you keep blowing, the balloon gets bigger and bigger, right? But there's a limit to how big it can get before it pops. That limit is determined by the strength of the balloon's material. Here's another one. Think about a car accelerating. As the car speeds up, it gets closer and closer to its top speed. That top speed is the limit. The car can't go any faster than that. Even in the world of finance, limits play a role. Imagine you're investing money and earning interest. The amount of money you earn will keep growing, but there's a limit to how fast it can grow determined by the interest rate. As you can see, limits are all around us. They help us understand the boundaries and possibilities of the world we live in. Now that we have a general idea of what limits are, let's get a little more specific. When we talk about approaching a limit, we're talking about getting closer and closer to a specific input value, but not necessarily reaching it. Think of it like walking towards a wall. You can take smaller and smaller steps, getting closer and closer to the wall without actually bumping into it. That's what we're doing when we approach a limit. In mathematical terms, we use the notation lim to represent a limit. For example, if we want to find the limit of a function f(x) as x approaches 2, we would write it like this: lim x2 fx. Remember, the limit doesn't tell us what happens at the specific input value, in this case x equals 2. It tells us what happens as we get closer and closer to that value, like a sneak preview of what the function is doing. Sometimes we're only interested in what happens to a function as we approach a limit from a specific direction. That's where right-hand and left-hand limits come in. A right-hand limit tells us what happens to the function as we approach the input value from the right side or the positive side. Think of it like walking towards that wall again, but this time you can only approach it from the right. We use a slightly different notation for right-hand limits. Instead of just an arrow, we use a plus sign, plus, as a superscript to indicate that we're approaching from the right. So, the right-hand limit of fx as x approaches 2 would be written as lim x2 plus fx. Right-hand limits are helpful when we're dealing with functions that have different behaviors depending on which direction we're coming from. It's like having a secret code to unlock the function's secrets. Section 5, left-hand limits coming from the other direction. You guessed it, left-hand limits are the opposite of right-hand limits. They tell us what happens to the function as we approach the input value from the left side or the negative side. Going back to our wall analogy, this time you can only approach the wall from the left side. You're still getting closer and closer to the wall, just from a different direction. To indicate a left-hand limit, we use a minus sign as a superscript instead of a plus sign. So, the left-hand limit of f of x as x approaches 2 would be written as lim as x approaches 2 from the left of f of x. Left-hand limits are just as important as right-hand limits, especially when we're trying to get a complete picture of how a function behaves. They're like the other half of the puzzle. Section 6, limits and continuity, a seamless connection. Limits and continuity are closely related concepts in calculus. In simple terms, a function is continuous at a point if we can draw its graph through that point without lifting our pen. Now, how do limits fit into this? Well, for a function to be continuous at a point, 3 conditions must be met. First, the function must be defined at that point. Second, the left-hand limit and the right-hand limit as x approaches that point must both exist and be equal. And third, the value of the function at that point must be equal to the limit. If any of these conditions fail, the function is said to be discontinuous at that point. Imagine a jump in the graph. You'd have to lift your pen to continue drawing. Section 7. The importance of limits in calculus. Limits are fundamental to calculus. They form the bedrock upon which other crucial concepts are built, such as derivatives and integrals. Derivatives, which measure a function's instantaneous rate of change, rely heavily on limits. Essentially, a derivative is the limit of the slope of a secant line as it approaches the tangent line at a point on the function's graph. Similarly, integrals, which calculate the area under a curve, are defined using limits. We can approximate the area under a curve by summing the areas of infinitely many rectangles under the curve. The integral is then the limit of this sum as the width of the rectangles approaches zero. Without a solid understanding of limits, grasping these more advanced calculus concepts becomes much harder. Section 8. Applications of limits beyond calculus. The applications of limits extend far beyond the realm of calculus. They pop up in various fields, including physics, engineering, economics, and computer science. In physics, limits help analyze the behavior of objects in motion. For example, we can use limits to determine the velocity of an object at a specific instant by calculating the limit of its average velocity over shorter and shorter time intervals. Engineers use limits to model and analyze systems with continuous change, such as electrical circuits and fluid dynamics. Limits help them understand how these systems behave under different conditions and optimize their designs. Economics utilizes limits to study concepts like marginal cost and marginal revenue, which are essential for making production and pricing decisions. By analyzing the limits of these functions, economists can determine the optimal level of output for a firm. These are just a few examples of how limits play a vital role in diverse fields. Their ability to describe and analyze continuous change makes them an indispensable tool for understanding and solving real-world problems. Section 9. Conclusion. Limits are everywhere. From the way objects move to the growth of investments, limits are all around us. They help us understand the boundaries and possibilities of the world we live in. By mastering the concept of limits, we gain a powerful tool for analyzing change and making predictions. Whether we're exploring the intricacies of calculus or unraveling the mysteries of the universe, limits provide us with a framework for understanding how things work. So the next time you encounter a limit, don't shy away. Embrace the challenge and remember, limits are our friends. They help us make sense of the world, one tiny step at a time.